All right. Online world is with us. 2 o'clock. Welcome back to your favorite class. Yes. Okay. Announcements. Really just one. Got homework number 1, which is due next Tuesday. After today's lecture, you'll definitely have all of the tools to tackle that homework. So go ahead and get started on that sometime soon over the weekend, I guess, if you haven't done it already. If you're having problems, again, office hours every single day, 8 to 9:30. Come visit me on Teams and say hi. How do we like the meme today? This is definitely true. Even when I'm like making homeworks or whatever, it'll be like 4 plus 7. I'm like, oh, gotta go to the calculator. Better go to the calculator. Make sure. It's definitely true. It's just like this reliance on it. If I don't have my calculator and I'm trying to do something, I'm just like, I can't even do it. Like, if it's at home and I'm at the office and I have my calculator, I'm like, oh, I guess I can't even do it. Even though there's like MATLAB and cell phone and stuff. I'm calculator reliant. The thing has been with me since I was your age. I've had my calculator for like 20 years. All right. Let's pick up where we left off. So I'll just remind you kind of where we were yesterday. We finished up with an example problem where we were looking at using our new unit vector addition strategy, right? So resolving our vectors into x and y directions and writing them in terms of unit vectors I hat and j hat, and then doing math on those individual vectors by adding the contributions in I, adding the contributions in j, to get a fully resolved force. Here we called it the vector capital R, and determining what the contributions in the I and the j directions are for this particular resultant. Then we can use our square root of the sum of the squares to determine what the magnitude of that, and we can also calculate what the angle that this resultant vector makes with the horizontal using traditional trigonometry. Here, the tangent function of the opposite over the adjacent, giving us this angle of 35 degrees. So this was kind of like the second go around that we did for this problem. The first was tip to tail, and that method kind of has its limitations. And so yesterday we talked about how to overcome some of those limitations by introducing the concept of unit vectors. And I want to do one last problem with these unit vectors before we move on to the next topic that is a little bit more advanced, and you'll see the power of unit vectors here, because if you tried to do this problem using like the tip to tail method, you would cry a lot of tears. All right. So let's do one last example, a little bit more complicated example, and I'll bring that into the shot now. So we have this more complicated example here now, and this is reminiscent of what is the last problem on your homework. So you have a homework problem that is very similar to this. You've got 3 forces that are acting on this bracket, which are kind of shown. Here we have a little bit of an interesting problem in that we have 2 of the 3 forces that are known, the 4 kilonewton and 6 kilonewton are known, but we're asked what is the direction and magnitude of the force F, that sort of unknown force there in the middle, that would cause us to have a resultant force that is 8 kilonewtons along this x prime axis. It's really kind of an interesting problem. This could come up in real life if you are hoping to direct the force in some particular direction, right, of some series of resultant forces. You want to apply force somewhere else so that you're moving an object in a certain direction, let's say. So we want the resultant force to be in that x prime direction and be 8. I'll give you a second here and then we'll work on it. I know it takes a little while to kind of like draw these pictures, so. If you're done drawing, I want you to think about how horrible this problem would be if you were doing the tip to tail method. Just think about it. Don't know that angle theta, don't know the magnitude of F. Oh, it would be a nightmare. Okay, so I'll copy this over to the writing pad here, and we'll work on it. So here's my picture. And here's the general problem statement is what vector F will cause resultant R, which is 8 kilonewtons along x prime axis. It's kind of the problem that we're trying to solve here, okay? All right, so we've kind of worked on problems like this already. We're gonna more or less assume that this force plus this force plus this force, when added together, are gonna give us some resultant, and that what we want that resultant to be directed along this x prime axis here, and we want it to be of magnitude 8 kilonewtons. Okay, that's kind of what we're after for this particular problem. All right, so we know the following is generally true. That the resultant force is what would be like force number 1 plus force number 2 plus force number 3. So let's put some labelings on these forces to help us sort of define what they are, and we'll go from there. So let's call this force on the left here, let's just call it force number 1. We'll call this force here force number 2, and this force here, let's call this force number 3. So our resultant is going to be a combination of those 3 guys added together. So the general strategy here is that we want to resolve sort of the forces that we know into the I and the J directions, and then add the contributions in I and J and solve for what sort of force F2 would be required to get everything to sort of like fall out and work out nicely. All right. Now we have to think about the things that we know in this problem. We actually kind of quote unquote know what our resultant force is. So I would give this guy like a check mark. I know what I want that to be. Okay, it's 8 kilonewtons directed at that 30 degrees to the horizontal. So I kind of know what that is. F1, I know what that is. F3, I know what that is. All right, so those are all things that I kind of know. This guy here is really my unknown. This is my question mark F2. So let's get down a little bit more information about the things that we know. We'll start with the resultant force. We know that we want the magnitude of the resultant to be 8 kilonewtons, and we want this to be at 30 degrees with horizontal. All right. So let's write this in our sort of unit vector fashion. Remember that our resultant force is like the magnitude of the resultant multiplied by cosine theta is the contribution in I, plus the magnitude of the resultant sine theta J. And so the triangle you kind of want to have in your head is, if this is like your resultant force here, then we're making or looking at this triangle, where this is like the resultant force Y, and this is like the resultant force X. Okay, so we're again just splitting this up into the X and Y components using the unit vectors I and J. Okay, so this would be like your Rx component, the unit vector in the X direction. This would be like your component of the resultant vector in the Y direction. All right, so let's do this. Here I know my resultant vector wants to be 8 kilonewtons, the magnitude. I multiply this by cosine 30 degrees in I hat, plus, again, my magnitude, 8 kilonewtons, multiplied by sine theta the j hat. And let's just put the 30 degrees in there. And so my resultant vector in the end should look something like 6.92 I hat plus 4 j hat kilonewtons. All right. That's where I kind of want to end up when I am done sort of adding my forces together. Remember, I also know F1. I can do the same for F1, F2, and F3. But this F2 is going to contain some unknowns. And those are the unknowns I'm sort of solving for. So let's do that. So F1, here, this is my force F1. It has a magnitude of 4 kilonewtons. And I can resolve it into the x and y directions using those 15 degrees. It will be like negative sine 15 in the x direction, since I'm pointed slightly in the negative x. And I will resolve it to the y direction with positive cosine 15. So here the force F1 is something like 4 kilonewtons times the sine of that angle, 15 degrees, and this is in the negative I hat direction. I'm going to add my resolution. Question.
Is there a particular reason why you prefer to have your negative unit vector as opposed to just doing like, sine and cosine of like 105?
The question is there a preference to using the negative unit vector instead of using like sine or cosine of 105? Either way is perfectly fine. If you want to attack this, instead of writing sine 15 with negative I, you could switch this for cosine 105 I hat, and you get the same thing. Either way works perfectly fine. I think it's just a little easier to sort of like resolve the triangle with like the 15 degrees. If you prefer to use like the 105 degrees, that's fine. You'll get the same answer. Okay, so continuing with my y component, here 4 kilonewtons times cosine 15 degrees in the j hat. Okay. With my force here F1, I'll have a slight negative component in I, so negative 1.04 I hat plus 3.86 j hat. All right, now on to F2. F2 is going to contain some unknowns that I'm going to sort of need to solve for in this problem. So let's just go through the same motions here, and we'll retain whatever unknowns that we have and sort of solve for them later. Okay, so here, F2, I'm going to have this magnitude of F2. And I'm going to resolve that into the, I'm going to still split this up into I and j components. And I'm going to resolve this force F2 into x and y components using this angle of theta. So here we'll have something like F2 times sine of theta in the I hat. And I'm going to add to that F2 cosine theta j hat. This is kind of as far as we can get with the vector F2. We've got two unknowns here, but we'll be able to solve for these later just fine. And we'll see how that happens. All right, we'll continue. Vector F3, similar idea. Here we've got this vector F3, but this guy is entirely in the x direction. So it'll be pretty sort of easy to see here that this vector F3 is just 6 kilonewtons in I hat. All right, so that one's pretty easy. All right, now I'm ready for sort of my vector addition to bring it all together. Again, remember my resultant force is like a summation of all of those individual forces. So finally, we're going to do my resultant force is F1 plus F2 plus F3. So let's write that down here. It's going to take a little bit of space, but we can do it. My resultant force is 6.92 I hat plus 4 J hat kilonewtons. This is going to be equal to F1, which is negative 1.04 I hat plus 3.86 J hat kilonewtons. That's my F1. I'm going to add to this F2, which again is just kind of a lot of unknowns at this point. It's this magnitude of F2 times the sine of theta in I plus the magnitude of F2 cosine theta in J hat. And I'm going to add to this my F3, which here is 6 kilonewtons in the x direction I hat. Okay, now here we have sort of an important lesson when it comes to vector math. And when it comes to vector math, the orthogonal directions, like the I direction, the J direction, and the K direction, the X, Y, and the Z directions, sort of like independent of each other, right? What do I mean by that? Well, things that are happening in like the X direction, we can sort of change the magnitude of the vectors in the X direction without changing anything associated with the Y direction. All right, it's whatever's going on in X is independent of what's happening in the Y direction. All right, same idea in the Y direction. I can sort of like scale and look at changes in values of the Y without affecting anything in the X direction. So we'll make a note here that these orthogonal directions are independent of each other. Okay. In traditional math speak, we would say that I and J vectors are a basis pair. When you get through with your advanced math classes, that'll make a little bit more sense, but it's sort of a pair of vectors that gives you a whole range of the two-dimensional space to work with. So what that means is we can investigate things that are happening in the X direction and things that are happening in the Y direction independently. Okay, so more on this later. So as a result, that vector equation that I wrote above, what actually looks like one equation, this guy here, this is actually two equations. All right, one equation in like the X direction and one equation in like the Y direction. So because these directions are independent of each other, we can analyze what's happening in X separately from what's happening in Y and vice versa. Okay, so this here is actually two equations. Two independent equations. One in X and one in Y. Okay, so let's look at what's happening in each one of these directions. So in the X direction, or what I'll say in like the I hat unit space, we're going to pull just the I components of each one of these particular vectors. So if we scroll up here, just going to pull like this guy here and the 6.92 value. We're going to pull the negative 1.04 value. We're going to pull this and we're going to pull this. All right, so we're just really focusing on what's happening in the X direction. as one particular equation. All right, so here in I, we're going to have something on the left-hand side like .92 kilonewtons equal to negative 1.04 kilonewtons. This is my contribution in the x direction for F1 plus the magnitude of F2 times the sine of theta. That's my contribution to the vector in the x direction from F2. And then here I have plus 6 kilonewtons. That's my contribution from F3. So I still have kind of two unknowns in this problem. That is the magnitude of the vector F2 and also the angle theta. But I could draw this down a little bit to make my life easier. And let's solve for one of these two variables. Let's solve for magnitude of F2. And you'll get that the magnitude of F2 in terms of the angle theta is going to be something like 1.96 divided by the sine of theta. Okay, let's call this like equation star. So we're going to have to come back to this. So we've sort of like investigated what's happening in the I direction here. We can also investigate what's happening in the J direction or the Y direction. So we'll do a similar thing for what's going on in sort of the Y direction. My contribution is 4 kilonewtons on the left-hand side. This is equal to my contribution in the Y direction from F1, which is 3.86 kilonewtons, and my contribution from F2, which again is an unknown, my magnitude of F2, times here the cosine of theta. And then F3, I don't have any contribution in the Y direction. All right, it was fully in the X. So if you want to put a plus 0 here, that's fine, but I don't have any contribution from F3. Okay. So I could take this down as well, and let's say solve for F2 again. So the magnitude of F2 here will be equal to 0.14 kilonewtons divided by cosine of theta. Let's call this double star. All right, so we're just kind of like using algebraic methods here. This is like a set of two linear equations. I guess they're not linear equations, but two equations and two unknowns, and we're just kind of working our way through using a substitution method to solve. Okay. So now we bring these together. And we're going to have something like, you can sort of work through this, but going to end up with something like 0.14 times the tangent. Well, let's just go through the whole thing. I'll just show it all. I'll bear it all. So up here we have this 1.96 sine theta equal to 0.14 over cosine theta. If we sort of brought the sine over to the right-hand side here, we'd have 0.14 sine theta over cosine theta, which is just 0.14 times tangent theta. And so we get to 1.96 is 0.14 times the tangent of theta. You can solve for this and find that the angle theta here is 86 degrees. It's interesting because our picture is quite misleading. All right. So the angle theta that we need for this particular force F2 is 86 degrees. If we go all the way back up to our picture, the picture makes it look like the angle theta is like 15 degrees. So it's a little strange, this particular picture, but you know, if theta was 86 degrees, then your F2 would have to be something like down here, you know? But the math is what the math is. So you just gotta roll with what the math tells you, all right? So we're not quite done yet. We got to take this and put it back into solve for a magnitude of F2. Let's say back into star or double star. And you get the magnitude of F2 is equal to 1.96 over the sine of 86 degrees. And you find that the magnitude of F2 here, 1.96 kilonewtons. Since the sine of 90 degrees is approximately equal to that, it sort of makes sense. All right. So this is kind of your final answer, that your force F2 would have to have a magnitude of 196 kilonewtons. It'd have to be directed at this angle of 86 degrees from the vertical, not from the horizontal. Okay, so that sort of concludes this problem. A little bit complicated, but if you had that force, then your resultant force would be directed along x prime with 8 kilonewtons. Interesting. All right, questions on this problem? A little bit complicated, but as long as you're kind of keeping your vectors straight and staying on with the math, it should be okay.
Dr. Hart, I do have one question.
Yep.
So just with the math that was in the beginning, if you want to scroll up, before you had been using cosine for the I direction and then sine in the J direction, unless I'm mistaken. Can you explain why it changed?
So the question is, I had been using cosine to resolve the vector into the x direction typically, and sine to resolve the y direction of the force. Why did we use sine for x and cosine for our force F2? Well, that comes back to the picture here. So the angle theta that was given in the problem here is this angle theta here. And so if I'm trying to resolve the force F2 into the x direction, I'm going to do that with the sine of that angle theta. So here, if I thought about like making my triangle for this force F, then the x component of this particular force, this is like F2 magnitude times the sine of theta. Right, so this is the x component of this particular vector. It just has to do with how theta is defined in this problem. Right, if theta were defined in this direction, then I would use the cosine function. Is that clear? Okay.
Yes.
Okay, other questions? All right, let us move on to the next set of notes. So I posted a new set of lecture notes on 2D equilibrium. So if you'd like to pull those up and follow along, you can do that now. All right, so let's talk about equilibrium of a particle. Okay, this one's pretty easy. A particle is said to be in equilibrium if the resultant force of all forces acting on that particle is 0. It's pretty easy. If the resultant force of all forces acting on that particle is 0. Right. So that's kind of the definition in English. The definition in math speak. We would say that a particle is in equilibrium if the following is true. The sum of the forces, this is a summation of the forces, which we know to be the resultant force we call capital R. If this is 0, then you are in equilibrium. This is kind of the basics for your statics class. Nothing is moving. It's in equilibrium. It's static. So you can do this summation using, use vector math, or tip to tail method. I mean, if it's maybe like a 2-vector system, tip to tail might be easy. Otherwise, you might have to go to a vector math sort of situation. So let me give you an example. I want to know, is this mess in equilibrium? Pretty hard to just kind of look at that and make a determination. I'll give you a second to copy that down if you're writing it. That's kind of the question that we're examining here. Is the summation of all of these forces equal to 0? Hard to just look at that and know. Sometimes it's obvious, but here, I don't know. You could maybe get out your ruler and try to do like the tip to tail to draw all these things together. That would be exciting, except it wouldn't. One little screw up in your angle or your scaling of your ruler, and you're not going to have a good day. But I'll show that if you were to use tip to tail method, you would have the following figure result. If you kind of like added these guys in order. So this goes back to sort of our original definition of vector math, tip to tail, tip to tail, tip to tail, adding all these things together. And interestingly, if you sort of like rearranged all these guys in a sort of a proper way, you could get a situation where you could show with the tip to tail method that F1 plus F2 plus F3 plus F4 did originally get you back to your sort of origin of this particular problem. So if you got your ruler out and you did this all perfectly, or you did it on a computer like SolidWorks or whatever, you could show that, yeah, with the tip to tail method, you do get back to 0, right? So yes, this is an equilibrium because the resultant force, which would be from point O to the end of vector 4, is 0. Remember, our resultant force is from our original particle to the sort of tip of the last vector in the series. Now, it's not really immediately obvious or easy to see that this would be true, so we may want to do some vector math to like verify this. Okay. So we would like to prove this with vector math. Okay. So let's talk about this with a little bit more detail. So remember that if the sum of our forces are equal to 0, then it would follow that the sum of the magnitude of the forces in the x and the I hat plus whatever forces we have in y. Let's make sure we're clear with magnitudes here. Magnitude of forces in the x direction in the I plus magnitude of forces that we have in y in the j hat would also be equal to 0. This is kind of our definition of our force. All right, it's whatever contribution we have in x in the I hat plus whatever contribution we have in y in the j hat, assuming we're in this like two-dimensional planar system. And if we distribute this summation, then we must have that the sum of the contributions in x plus the sum of the contributions in y in the j direction have to be equal to 0. We've already kind of talked about this, and since the I direction and j direction are orthogonal with each other, there's nothing that we can do in the I direction that will influence the j direction, okay? I can make all sorts of changes I want here in the x direction with my vectors in x, and it's not really going to change anything about this guy, right? Same thing in the y direction. I can apply forces in y all I want, but if the contribution here is not equal to 0, then I'm going to have a hard time sort of getting to a point of 0 resultant force. So my point here in English is that since I and j are orthogonal, or perpendicular if you like, then for equilibrium, the following must be true. That both of these conditions must be satisfied. The sum of the forces in the x direction must be equal to 0, and the sum of the forces in the y direction must be 0. Both of these things must be true. Because if we have some non-zero component of the force in x, there's nothing that we can do in y direction to overcome that. If we have some non-zero component of the force in y, there's nothing we can do in the x direction to overcome that, okay? So since these things are kind of like mutually independent of each other, they both have to be 0 for this to be true. All right, so let's verify our previous example using actual vector math. And I'll bring the picture back in here. It's just the same picture as before. Thought I was going to bring it back in here. There we go. And let's get this guy down on paper. All right. So after introducing what we know to be these unit vectors, which is like, you know, here's my I hat. Here is j hat, which represents sort of our unit vectors in the I and the j directions. We can write that F1 is 300 I hat pounds. F2 is negative 173.2 J hat pounds. It's only in the Y direction. F3 is 200 pounds, resolving into the I direction with sine 30. That's this angle here, plus 200 times cosine 30 and negative J. F4, 400 pounds times sine 30 in positive I hat, sorry, negative I hat, adding to this 400 pounds times cosine 30, and what is the positive J direction. All right, I can investigate just the X and Y directions independently, so I might want to do that. So we see like X components here of like 300. There's no X component in this guy. I have an X component here of like negative 200 sine 30. And I have an X component here of like negative 400 sine 30. So if you just look at, let's say, the summation in the X direction. Oh, my battery's running low. Hopefully I can get through this before it dies. So here, summation of the forces in X is like this. 300 pounds minus 200 times sine 30. That's coming from F3 minus 400 sine 30. And my question is, does this equal 0? Kind of what I'm trying to define with my math. And you could work this out. This will be 300 minus 100 minus 200, which does in fact equal 0. So my summation of forces in X equal to 0 has been satisfied. And I can do the same thing in the Y direction. Here in the Y direction, I've got this negative contribution, negative 173. I've got negative 200 cosine 30, and I've got 400 cosine 30. So here, this is something like negative. Sometimes I touch the thing for a different marker change and it doesn't go. Negative 173.2 minus 200 times cosine 30. Here now plus 400 cosine 30. I want to know, does this equal to 0? Here, negative 173.2 minus 173.2, ironically. Here, plus 346.4. This does equal 0. And I verified it using algebra. It's a lot safer to go this way than like the tip to tail method, getting your ruler out and doing all the angles. All right. So because both X and Y, so since sum of the forces in X equals 0 and sum of the forces in Y equals 0, we do have equilibrium. Okay. So that'll do it today. When we come back on Tuesday, we'll introduce free body diagrams, probably the most important concept of this class. So that's it for today. Work on your homework. Come see me in office hours if you got problems. Otherwise, have a nice weekend.